Okay, now for the second task, this is the example number 1. We have the same headers and the one function. This function would have two variables. One is obviously integer I and another is integer n. 9 value have been set for the integer n, and we have also created a variable to set the number of threads over here of OpenMP. Actually, this function is creating the number of threads that we are passing the value, that is 4. We are using the same pragma OMP parallel and having two extra clauses, that is shared and private. We are passing n in shared. The shared function will actually make that passed variable shared among all the available threads. Means every thread would access and update the shared value. And for private, this I value would be different for different threads. That is, every thread would have its own value of I. Okay, after that we have used pragma OMP for, in which we are actually applying the for loop. Pragma OMP for is a for loop clause. Its work is to provide the chunks to the threads, whose work is to determine which iteration would be provided to which particular thread. For example, in this problem we have 4 threads and 9 iterations from 0 to 8. So at least 2 iterations would be assigned to each thread, and the remaining one would going to be assigned randomly to any thread, particularly that thread who will complete its work first. We will show in output that which thread have executed which iteration. So we will build in the similar fashion that we have already did. Now this will build, and now we will run. So then we will get output. We are doing that thread 0 have created 3 instances, 0, 1, 2, whereas thread 3 created 2 instances, 7 or 8. Thread 2 run 2 iterations, that is 5 and 6, and thread 1 created 2 iterations, 3 and 4. So from 0 to 8 all iterations run. Now we will see the same code in another fashion. We will not take separate parallel and for loop that we have already did previously. We can also combine this syntax, calling it as parallel for. And when we will use this syntax, then we do not need to use this shared and private variable. Beauty of this clause is that whatever the predefined values are, that is here n is, it will make it by default shared, and the value which is not defined, that is I here, that will be declared as private for each thread. Let me delete the output file and recompile it. And then we'll execute again. So you will find the result similar. That is thread 0, 0, 1, 2 iterations, thread 2 perform 5, 6 iterations, 1 did 3 and 4, and 3 did 7 and 8. So your output could be different because it's random number of iterations which belongs to which particular thread. So output of all the students would be directly different. If you will compare with the previous, the thread 1, the 3 and 4, and here the thread 1 also performed 3 and 4. So this could even also different among your own 2 times program run. Okay, students. Achha, this is example number 2, but it is similar to example number 1. The difference is that we have only added a variable a, to which we are updating in the loop as well, and we are also printing the value of that variable with the thread. So as I and a are not defined, so we are taking it as private. So I by default would be private and a private and n shared. But if we will not declare a as private, then in few test runs a will give the wrong response, but in some it gives the right response. You may also test it by yourself. For example, for a dry run, if you will remove it and we will run it, so we will check it out whether it's coming right or not. So let's compile it. So if we will run it, so हमारे पास आंसर सही आ रहा है. So A is getting 1, 2, 3, 4, 5, 6. So mostly answer is usually right, but in this case also happened that A is equals to 2 and I haven't arrived, and A is equals to 6 value repeated. So this could happen whenever you haven't defined it as private, to avoid any kind of error. Okay, so define it as private. So as already discussed, that the pragma itself make those variables already private, those who are not defined previously. So explicitly for for loop, it's a bad practice to define it as private. So here we were having 6 iterations and 4 number of threads. So each thread will get one iteration 0, 2, 3, 1, and the remaining iterations would be given to thread number 0 and thread number 1. So whoever thread will execute first will get this remaining number of iteration. Okay, students. Now we have example number 3. It is similar to the previous examples, in which A have been taken as an array of 6 elements and we have passed all zeros in that. Here the loop that we are getting of parallel for, here we have defined variable A as shared, as this was as in array format, so better is to define it, otherwise as it was defined, so by default it could be considered as shared. Actually what's happening in the loop, that ith element is equals to a ith plus ith value. It's a simple thing that on incremental basis a value would going to be added and it will going to be displayed and will replace here. Technically this work will run in parallel using threads, and when it will going to be completed, then a array will going to be print. Make sure that this display would be sequential. But after running this code, we will came to know that there would be no errors inshallah, because we have used the shared variable. And the parallel for loop automatically will make the I variable private and handle it properly. So if we will going to run this, पहले हम इसको compile करते हैं, then we will run it, then we will get the answer. In 0 we have 0, in 1 we have 1, in 2 we have 2, in 3 we have 3, and so on. So shared variables are working in such fashion that they would going to be accessible by every thread. So as we are accessing with a private variable, so our output is now correct, not performing any wrong thing. Okay students. Okay, now this is example number 4. We have used the same headers and we have created 2 variables and one sum variable as well. If we will come on this line, we have already studied pragma OMP parallel for, but we have a new clause default shared over here. Default shared is enabled by default. Even if we don't write it, it will work. What it does, that it do for whatever the variable that is not specified, that is it is private or shared, then it will make that variable shared by default. In this case we have 3 variables and we have specified I as private variable. In this way it will take n and sum as shared variable. As I already explained this in example number 1, that n was by default shared. I wasn't being shared because it was using under the loop, so pragma was taking it as private automatically. But in this case, as we have sum as well, so we have written it. If you don't write it, it will work in the same way. In this case, we are running a for loop and updating the sum variable. So issue can arrive if the sum is a shared variable. So it might possible that 2 threads that are working together, it's obvious that their addition number would be different. It might possible that their addition result would be wrong. Ideally, the answer should come this, as we have 6 iterations, so answer must be 15. But in case of any issue, this answer could be disturbed. If we will run this code, so we are getting the answer 15. So we found that all threads execute one by one and we got the correct answer. But if our system is busy and handling the multiple threads at the same time and 2 threads executed simultaneously, then if this shared default couldn't tackle in the same way, so the answer could come wrong. So it's not ideal that we are updating the shared variable under the pragma loop. That may cause wrong results. Okay students. Okay, now this is example number 5 using the similar headers again. We just have 2 variables over here, I and index. Index is initialized by 4. Number of threads are 4 and we are using pragma OMP parallel here only, and we are not applying any loop. Here we have a new clause that is first private. Whatever the variable we will pass in the first private clause or function, that assign that variable value to each thread. This is actually rarely used because by default that indexing we use usually starts from 0. But in this case we have started from 4 and in this block there are 4 threads and 4 indexes. So every thread number will add up with an index number and will display. So now if we will run it, so now we had index 4 plus 0, answer is 4. When index was 4, thread number was 2, answer is 6. Index was again 4, then thread number was 1, answer is 5. Then 4 plus 3 is 7. Here we have executed 4 threads. There we have add on the index value into the thread value, because everybody was having individual value of index, which was 4, which that's why it's not incremented, but 4 added on in that thread ID and have been displayed. Okay students. Okay, this is example number 6. Here we have taken integer I and one integer n, that is number of iterations, and we have taken a variable a which is being set as -1. Here we are using for loop of pragma OMP parallel, where we have defined I as private. It was not needed, but just for practice I have done this. But we have used last private new clause. Its purpose is when the loop will complete its iterations, whatever will be the last iteration, it will store that value of the variable into that a. In our that for loop, a is getting I plus 1. Whatever will be the last iteration and whatever will be the last iteration value of a, as we are moving from 0 to 5, so 5 plus 1, that is a value 6 would be the last value. So ideally its answer would be 6. It might possible 5 iteration would run first and 4 would be later on, and if iteration 4 would be running at the last, so in this case its a's answer would be 5. But this thing may differ from processor to processor, also depend on the busy schedule and idleness of the processor. So in this case most likely the answer would be 6. Let's run this code. So we got the answer 6, as the last iteration was 5 and 5 plus 1 is 6. And as a minus 1 value have been accrued because we have used last private value. So by any means loop last value have been returned. Okay students. Okay, now this is example number 7. We have used the same header again and a main function, as we are using multiple clauses in this example. At the start we have defined few variables, I for loops, number of iterations, and n. Particular chunk size is 2, that would going to be used in scheduling later on. We have defined 2 arrays of type float a and b and a result variable. This is our starting loop where we are generating our arrays. Array a will have values with increment by 1. In array b would be double than array a. We have set number of threads as 4. Here we are using pragma OMP parallel for. Here first clause we use is of default shared, which tells that whatever the variables are being used in for, unless not defined as private, would remain shared. Here as we defined I as private, so result would going to be shared. If we will going to see only this part, so this result could come wrong. As already discussed, the result is a shared variable, and if the race condition have been applied, that is wrongly updated by the wrong resource, could apply the race condition. As a and b are using the private variable I, so their product would always be correct, but in result overwriting could be done. So to counter this part, we have used reduction. What's the task of reduction is whatever the variable we will pass in reduction, its value would going to be calculated after the loop run. As we have given the positive sign over here, which means we performed addition for all the individual values of the result in the loop, would going to be add. So this reduction would actually technically make the result as a private variable and will provide its result at the end. Means however number of threads would going to update the result value would going to be stored at one place in a memory. After that the result that we have initiated on is defined by 0. So results value of every thread would going to be combined due to this operator of plus, and then at the end would going to be stored in a result. In this way a compiled consolidated correct value of result would going to be arrived. In a similar fashion we have used scheduling. By default scheduling is done by pragma itself, but by using static we can modify this according to our wish. First argument of scheduling is either static or dynamic. In static, before the run of the loop, fragment divide the data into chunks of the number of tasks to be provided to the threads and will hand over to the multiple threads. Knowledge basically being done before the start of the loop. And in dynamic, Pragma will provide the task to all the threads at the start. If any of the thread during the loop becomes idle, it will ask the another task during the loop. For example, if a thread is running who have been assigned 2 tasks at the start of the loop, and as soon as it will complete both the tasks, from the remaining number of tasks, it will ask the task from the pragma. But in static, all the tasks would going to be divided into chunk and would going to be provided to all the threads, and it would be fixed. But in dynamic, it wouldn't be fixed. Chunk is basically the chunk size. Here we have chunk size 2, means how many iterations should be provided to each thread. In this case, we have 4 threads and we have 10 iterations. We will make the chunk of size 2 each, and we will have 5 chunks in total. Means 4 chunks would going to be provided to each thread, and the remaining end chunk would going to be taken by any one thread. So as we are printing this result, so final output be hopefully would be correct now, as we have used reduction for our result. Now let's run this code. So its answer should be 570. Check it out, you are viewing 570 as a result. Okay, now this is example number 8. Same headers again. In a main function we have 2 variables, similar variable I and similar variable n for the number of iterations as we did, and we have taken number of threads as 4 again here. To discuss another concept, we have separated out parallel and for part of code separately. At the start, we are using OMP parallel, where we have given a private variable I. And make sure this whole block is of parallel block, including this print line, okay? And another block we have where we are running the for loop, in which we have used a new clause, no wait. The purpose of using the no wait clause is the way Pragma works, that it creates the stream of threads, and after that it will going to execute it and will compile the result of all the threads, will display it. No wait actually remove those waiting conditions that thread uses in between the tasks. Just like after thread creation there would be thread execution, and then after that there would be the thread joining. So whatever the waiting time would be in between of their synchronization would going to be removed. It might possible that one thread would going to print this line, and then another thread would going to print this line, and meanwhile any other thread will print this outer block line of printing after completion of its loop. So unsynchronization behavior could occur. If we will do this without no wait, then all the threads will print in line their for loop response, and after that they will print this outer print that these thread numbers are after the loop. If we will going to run it, now we can see that when thread 0 run, as soon as it's completed its execution, we haven't wait for the other threads and came out of the loop and print out this outer loop statement. Similarly, when thread 3 completed its run for its 2 iterations and it come out of the loop and then printed this outer loop statement. Similarly, thread 2 did this task and then thread 1 this task. Make sure that sometimes this could happen. A thread who is printing its iteration, for example, let me take example of thread 3. Thread 3 after iteration number 6, it might possible that it could go in hold state due to processor busy or any other kind of problem. So meanwhile, if other threads, that is thread 2 and 0 and 1 would going to be executing, meanwhile the thread number 3 would wait wherever it was hold, while the rest of the threads wouldn't wait for thread number 3 and will carry on their execution. So practically we run this program many times, so we also found an output in such a way that thread 0, these 3 lines were similar, then thread 3 with loop iteration number 6 appeared. After that these 2 lines, that is thread 3 iteration 7 and thread 3 after loop, these were not printing over that same place. Then thread 2 and thread 1 have taken its place in output, means thread 2 completed first, then thread 1 completed first, and these 2 lines printed at the last. This is showing how no waits actually work. Actually no wait removes the restriction of the waiting, but obviously would run in order the way 0 run first, then 1 executed later because it's an order of iteration. In this way 6 run first, then 7, but make sure threads can interchange among themselves because of waiting conditions. That is one part of the thread 3 first, then another part of the thread 2, then thread 3 other parts. All this depends on the processor speed. As we do not have any other workload, so answer is coming similar, but difference could arrive.